All right, so we're going to look at inverse function differentiation, and sometimes this can be really useful to solve a bunch of different problems. So some prior knowledge in order to understand this lecture will be just differentiation, which was the previous one, because we're sort of building on sort of core differentiation concepts. Functions and their inverses as well, so a solid understanding from methods about functions and their inverses, a bit of understanding of the chain rule will be helpful, and the concept of the derivative as a rate of change. So dy dx as the slope of a tangent line at a point. So sort of first principles type stuff about, fundamentally what is differentiation. It's analysis of change. So that sort of stuff. And a pretty short lecture in some ways, but we're just going to look at the derivative of x equals f of y. So when x is a function of y rather than y being a function of x, which we're more typically used to. And then we'll look at an application problem which can sort of put into perspective why this might be relevant. So we will do all that. So let's jump into it. So the first thing is to talk about sort of the big idea, which is that if we're trying to find the derivative of x equals f of y, well, sure enough, we can take the reciprocal. So if we can say that dy dx is equal to 1 over dx dy, as long as dx dy is not equal to 0. So you should see that and you should be like, why on earth is that true? Because that's certainly my first reaction. But remember, we really can, in some ways, think of dy dx as a fraction, as long as we have some conditions that we're satisfying. And in this case, the condition we need is that x equals f of y is a one-to-one function. So let's break this idea down a little bit. Imagine we have this function y equals f of x here. And you can see we've got sort of a secant between this point and this point up here. And this m value is just the average rate of change between those 2 points. Okay, so you could sort of think about it like this. That's just rise over run. So dy, change in y over change in x for this secant at the moment. And as we change that, the value of that gradient changes for this graph, right? So you could imagine if we were to find the inverse function and make x a function of y, so sort of swap all of the x values and all the y values, so that would be the inverse function, right? If you swap all the x values and y values, you get this graph over here, which is the inverse function, and that's reflected in the line y equals x. And sure enough, what you end up with is that the gradient of this line is 1 over the gradient of this line. So you'll see 1 divided by 1.09 is 0.92. And sure enough, as we move it, you can get a calculator out and check it, but 1 divided by 1.04 is 0.96. And it should be obvious when we go to 1, because 1 divided by 1 is 1. So you end up with this situation, which is interesting. So you can sort of say that this holds true for when y equals f of x is a one-to-one function, or similarly x equals f of y is a one-to-one function, which a lot of things are. A lot of application style problems are one-to-one functions, so that's useful. And just to really reiterate, you've swapped dx and dy, right? So what was the rise here is now equivalent to the run over here. And so you've swapped it. So you can say 1 over dx dy equals dy dx. So that's that's at least how I think about it. Because you should be looking at this and being like, is that true? Because this represents the derivative, but it does represent a fraction if you think about it carefully and place certain restrictions on things. So that's a very useful tool, because we'll see in this next application problem, sometimes it's easier to find dx dy, and then you can just do 1 over it to find dy dx. So let's talk about that in terms of rates of change. So let's have a look here. So we've got an application problem and gasoline flow in a pipe. So let's just have a read. So a technician is monitoring the flow of gasoline through a pipe. The volume of gasoline in litres, V, flowing through the pipe is measured as a function of pressure, and pressure is measured in pascals. And the relationship is given by the pressure is equal to 1,000 plus 200 multiplied by the square root of V. Find dP dV, the rate of change of pressure with respect to time. So this question here should hopefully not be too daunting for you. You're basically asking yourself, for a given change in the volume of the gasoline flowing through the pipe, what change does that give us in the amount of pressure that's being applied? And so if we do the maths on that, we're just finding the derivative, and hopefully you're pretty comfortable with that. You can whack it in your calculator and you'll get that dp dv, the change in pressure over change in volume, is 1,000 divided by root v. Okay, so we're just going to put that there for now, just so we can recall it. Okay, then we're going to look at the next question. So find dv dp, the rate of change of volume with respect to pressure, without directly differentiating v with respect to p. So what that means is we can use the identity from before, that dv dp is going to be 1 over dp dv. And so we just do 1 over that, so it's the reciprocal, so it just flips it. So it becomes root v on 100. And now we can actually think to ourselves, all right, well, why is that relevant? So explain in practical terms what dv dp tells us in this context. And yeah, well, let's do that. So dv dp measures how much the volume of gasoline changes per unit of pressure added. So the change in volume given a change in pressure. And in this context, that's actually more interesting than the derivative, because it's more meaningful because engineers control the pressure, and that influences the flow, which determines how much volume travels through the pipe for a given amount of time. And so it tells us how responsive the system is to pressure changes, and that's important if you need to regulate the flow. So because the engineers are changing the pressure, the VDP is actually more interesting. Now, sorry, I should say dVdP. I think I hopefully said that right. Now, the other way, dPdV, we can say that this is mathematically valid, but it's less practical unless you're designing a control system that reacts to flow, because this is telling us how much the pressure needs to change to produce a change in volume. Okay, so this is telling us, sort of a different situation. So this tells us how much the pressure would need to change to produce. So given some change in volume, how much did the pressure change? And that's, while it's valid, it's not as useful because what the engineers can control is pressure. So it's a bit more complex than sort of your usual just taking a derivative, but you can see here why it might be relevant for practical situations. Let's have a think about, to really wrap our head around what's going on, let's have a think about what the graph looks like. So we're just going to graph pressure and volume here. So on the x-axis we've got V, and on the y-axis we've got pressure. So we can see here that the pressure required is 21,000 pascals, and you'll get 10,000 litres flowing through the pipe in a given amount of time. So yeah, and then obviously it changes. You can see, interestingly, down here, that for a given change in volume, down here you get a larger change in pressure for smaller volumes. So early on, to get a small change in volume, you need a large change in pressure. But yeah, you can see the gradient sort of flattens out later on. So yeah, that's the original graph. And now what we're going to do is we're not just going to graph the gradient, we're going to graph the reciprocal of the gradient, which is the inverse. So we're going to graph dVdP, which we worked out before was a square root of V on 100. So this is what this graph looks like, and it's a bit tricky to sort of understand what's going on here, but let's just pick a value. Let's pick around 10,000. Okay, there we go, nice and easy. So what this number is saying, and I encourage you to think about it, but it's saying that when the volume of gasoline flowing through the pipe is 10,000 litres, the change in volume divided by the change in pressure is 1. So what that means is to get you would need to increase the pressure by 1 pascal to get 10,000 let me think. All right, I just wanted to make sure that I phrased it properly. So yeah, at a volume of 10,000 litres, the rate of change of volume with respect to pressure is 1 litre per pascal, which you can see because that's the units on the y-axis, right? So that means for every 1 pascal increase in pressure, you get an additional 1 litre of gasoline flowing through the pipe. So that's the meaning of this dVdP, which is the reciprocal of the gradient of the original function. So yeah, which is more meaningful for the engineers because they are able to change the pressure. So yeah, for every 1 pascal increase in pressure, For every 1 Pascal increase in pressure, you get an additional 1 litre of gasoline throwing through the pipes. That's the rate of change of volume with respect to pressure at 10,000 litres of volume. So a little bit more tricky than your typical differentiation question, but hopefully you can see why it's relevant. If you found that useful, give us a thumbs up. Let us know how you're going. If you have any questions, let me know. And if you need any private tutoring, let me know as well. So good luck with everything you're doing, and I'll talk to you soon.